In this section, we're going to cover digital data modulation techniques. In particular, we're going to cover three of the more popular kind called amplitude shift keying, frequency shift keying, and phase shift keying. The first one, amplitude shift keying, is nothing more than a form of data modulation where you represent the digital data as variations in the amplitude of the carrier wave. The simplest form of this is called on-off shift keying and is represented up here in the upper right-hand corner of the diagram. In this case, a digital bit of 1 is represented by an amplitude modulation on the carrier signal of level 1. A 0 is represented by no modulation. 1 again represented by modulating the carrier to a level 1, etc. There are other forms of amplitude shift keying, such as this 4-level encoding scheme shown down here, where 2 bits of data are encoded with each of our symbols. In this case, the bits 1, 0 are represented by a level 3 modulation. The bits 1, 1 are represented by level 4, etc. Now, amplitude shift keying is a fairly simple form of digital data modulation. It does have its drawbacks, though. Like AM radio, it is very susceptible to atmospheric noise, distortions, and other propagation conditions that will affect the amplitude of the signal. That's why this type of modulation is typically used today only over optical fiber transmission, where you're not susceptible to those types of distortions. So to better understand amplitude shift keying, let's go ahead and work an exercise. In this case, we're going to be looking at on-off keying. So we'll go ahead and we'll bring up our GNU radio companion again, and we'll look for our 300 megahertz signal. This signal contains an amplitude shift key set of digital data in it. So we're going to look at recovering that signal, and then also trying to determine what the dip switch settings are of the garage door opener. So let's go ahead and bring up our GNU radio companion, which you see right here. This is essentially the same, these blocks here are the same blocks we had before when we were looking at the externals of the signal, where we had our file source, which is our 300 megahertz signal, a multiplier just to get the signal levels up, throttle, and then also our FFT sync to display the frequency domain of the signal. What I've added to that, a scope sync, which will display a time-based variation of the signal, and then also before that I converted to a real number, so we're only looking at the real part of the signal. So let's go ahead and start that up. And that should come up here, and there we go. There's our signal again. If we look down here, we'll see, go ahead and put peak hold on, we'll see, yep, there's our signal. Looks very much like the same signal we were looking at before. Now up here in the upper plot, that's our time-based scope sync, which shows a signal with no modulation on it, followed by a period of time where the signal is modulated, has an amplitude modulation to it. And so this is clearly an amplitude modulated signal coming out of our garage door opener. So let's go ahead and stop that, and we'll go ahead and activate these other parts of our GNU radio. The first thing we're going to do is we're going to convert our complex number to just the magnitude. So again, all I'm going to be interested in here is the magnitude of the signal that's being present. I'm going to threshold that then, so that if the signal is above a certain threshold, I'm going to output a 1. If it's below a threshold, I'm going to output a 0. I'll use these 3 components to recover my digital signal. So if I go ahead and enable those components, I'm going to disable my FFT display here just for real estate, screen real estate purposes. So we'll go ahead and start this up now, and the signal should come up here in just one moment. And here we go again. You see up here in our plot here, we're seeing that same real-time signal showing up, where we see a modulated signal followed by some period of time where there's no modulation on it. But now down here, this is our threshold signal, where we have what looks like a bit stream. And if I go ahead and stop that, I'm going to stop that so it doesn't disturb me, and we move that around, it looks like, yes, we have a bit stream captured here, where if we count those, we'll count 10 bits of information. And it's a series of short pulses followed by longer pulses. If I change the time scale up here to match the time scale I have down here, There we go, and stop that. I can go ahead and kind of line these up a little bit, and you can see that I modulate for a short pulse, short period of time, which corresponds to this short pulse, digital pulse, a longer period of time, which corresponds to this longer digital pulse, followed again by a short pulse, followed by no modulation for a while, a long pulse, etc. And so from this, we should be able to deduce what our dip switch setting is of our garage door opener that we recorded earlier. So let's go ahead. We'll stop our GNU radio here and go back. So really, I'd like, as part of the exercise here, why don't you go ahead and set up your GNU radios and determine what the dip switch setting is of the recorded garage door opener. We'll review the answer in the next chart.